Okay, I think we can go and get started. So welcome everybody to the Mars Perseverance landing event. My name is Joe Aiken. I'm the technical director of the Hotung Visualization Lab. I'm joined by my colleague, assistant professor in geology. This is Joe Levy. Joe Levy is actually a geomorphologist and planetary scientist with interest in sedimentary geology, surface processes, and geologic and ecological interactions. He focuses mainly on permafrost land systems around the world and around the solar system. And he has a lot of actually interest in this particular mission. So let me give it up for Joe Levy, and he can take it from here and introduce some of our panelists, some of the students.
Sure thing. Thank you so much, Joe. And thank you everyone for coming today. This is obviously a super exciting day. I'm glad to be with you all, getting ready for humans to send another robot onto Mars and to get what feels like people on Mars. I'm joined today by an outstanding team, not only Joe representing the Viz Lab, but also members of the Colgate Martians, some of the Cold Dirt Lab team. So you have Ian, Bronson, Ishraq, and Jessica here. And we're all going to be part of this landing event. So we have a bunch of things planned. In addition to actually watching the last minutes of the landing as everything unfolds, we also have some opportunities to learn a little bit more about Mars, to answer some trivia, and maybe most excitingly, to win some fabulous door prizes, including Mars rover Hot Wheels for the Perseverance mission, posters, and a grand prize that we'll be giving away as a door prize again just before landing. So let's get started. We're really lucky on this feed to have access to the Viz Lab and to the planetary visualization system in the Viz Lab. And so what we'll be doing today is having the NASA feed up in the corner, and then we'll be using some of the visualization tools at our disposal. And so this is actually following the trajectory of the Perseverance rover as it was launched about 7 months ago from Earth on its way to Mars. So we're now watching from the launch date. We're zooming back out in the solar system and getting ready to follow the trajectory of the spacecraft as it left Earth behind and went on its way towards Mars, which will eventually bring us up towards today. So just have to find ourselves in the solar system. There we go. All right. So that blue dot there is Earth and its orbit. Is that right, Joe? That doesn't look quite right. Or are we ready to launch? Okay, perfect.
Yeah.
All right, let's launch. Ishraq, we had talked the other day about the trajectory that the spacecraft is taking. So we can see it in the white line there. Anything you wanted to mention about the orbit that it's in right now?
Yeah, it's, as far as I know, it's a variation of the Hoffman transfer orbit, which kind of uses the initial kinetic energy from the planet itself that it takes off from. So the spacecraft is using the energy, like the kinetic energy of Earth on its orbit to kind of take off and get into an an eccentric elliptical orbit on its way towards connecting to the Martian orbit, which is a bit more, which is also an ellipse, but a bit circular.
Yeah, so this is really just like, two runners on a relay race trying to pass off the baton, where the baton is the Perseverance spacecraft. So we're trying to get the planets going as fast as they can on this race, and then throw or yeet or whatever is necessary this spacecraft on a rocket to rendezvous with Mars. And as you saw in that orbit transfer, Mars actually needed to catch up with the spacecraft. So what we're seeing today is not the spacecraft racing into Mars as fast as it can. We actually saw that the spacecraft overshot a little bit and is now falling back to rendezvous with Mars. So it's still closing at more than 10,000 kilometers an hour, but it is not. It's not racing to plunge in like a missile. It's just trying to rendezvous and start its entry, descent, and landing. And so we're going there to study the Martian surface. So why don't we head on down next to the Martian surface, Joe? This is not the first mission to Mars, and I just wanted to remind you of the previous series of rovers, the Mars exploration rovers, that have spent close to a decade exploring Mars. And you would be excused for thinking that we were looking at the Perseverance landing site in this view. You can see right in the middle of the view is Gusev crater, an enormous crater, and that thing snaking into the bottom of it that looks like, a giant canyon is just that. It's Maadim Vallis, which is a giant canyon on the surface of Mars, which cuts into Gusev crater. And so when the Spirit River was sent to Gusev crater, the idea was that it was a lake, that there was a channel flowing into this closed basin, and then water must have ponded there. And so the river was sent to check it out. And what did the river find? Basalt, lava rock. And this was a frustrating landing site. This probably was a lake deep in Martian history, but it's been capped with lava and with volcanic deposits that have sealed away any kind of evidence of Mars's warmer, wetter past. And so it's partially to overcome this shortcoming of that landing site that the Perseverance mission is heading to Jezero crater. So keep in mind this geometry, right? On Mars, a good place to have a lake is in the middle of a crater, and a good sign that it's a lake or was a lake in the past is a channel flowing into it. And now we'll go check out Jezero crater, which is Perseverance's target today. And we'll see what's similar and what's different about it. So we're moving around to the other side of the planet, just like Earth. Mars has sort of time zones depending on where the subsolar point is. So you need to get the lighting just right. You need to see what's going on. The Perseverance will be landing during daylight hours on Mars. And so, yeah, one thing I saw this morning in a tweet that was very exciting was that by the time the sun sets on Mars again, hopefully there will be another lander and rover on the surface. So here we are just lining up on Jezero crater, which is the large crater right in the middle of that field of view there. And we're looking at data that's provided by the Context Imager. This is a beautiful camera that's orbiting Mars right now. It's kind of like Landsat for Mars. So it takes big, bright images of the surface. Not the highest resolution. You couldn't read the rover's license plate with this data, but geologists love this kind of big, broad view. And hey, folks on the panel, what do you notice that's different about Jezero crater versus Gusev?
Would it be this giant delta formation that we're looking at right now?
Absolutely. So where the crater is breached there's a channel going off towards the left side, and that valley network has busted through the crater wall. And at some point in the past, this crater was filled with water. And we know it was filled with water because there's a giant delta at the end of that river channel, sort of like the Mississippi Delta or the Nile Delta. This is a place where the river entered the crater, entered the standing still body of water, and the sediment that was in the channel was left behind, making this big delta deposit. And geologists love geeking out about this delta. We see everything we see on Earth. We see channels that were moving back and forth. We see evidence of change over time. And hopefully, what we'll find in this delta, like we find in deltas all over Earth, is the remains of organic material. And so if there was ever any living thing on the surface of Mars, this is a pretty good candidate for where you might go to find it, preserved in this delta deposit. So that's why this crater was picked as the mission target today. Gusev is an absolutely stunning site. As we zoom out a little bit on it, you might be able to see just lost in sort of the mist on the other side is actually another channel which leaves the crater. So not only does Jezero crater have an inlet river, but it also has an outlet river. And so this is kind of like a bathtub that overflowed. We know that this crater had to be at least as filled with water as both of these valleys. And so this is a really big lake. Jezero crater is actually named after a village on Earth, which has a beautiful lake in it. And actually, I believe means lake. So this is a place where NASA is banking a lot on finding some lake sediments. And so we are all pretty excited about it. With that introduction out of the way, I think we have some more excitement, and that is our first series of door prizes and trivia questions coming up. So go ahead.
Yeah, so for the Hot Wheels Perseverance rover model, we have Aaron Llewellyn, Howard Powell, and Leon Nichols as winners.
Obviously, we are here at Colgate University. We have people tuning in from all over the country and actually all over the world. So welcome. If you are a door prize winner, we have your registration email. And so we'll be getting in touch about how to send you these really cool things. This is your own miniature Perseverance. Perseverance is actually the size of sort of a pickup truck. It's a pretty big rover. So this is definitely, Matchbox is the right scale for thinking about this rover. Let's move on to some trivia. So as folks have questions during the course of this event, feel free to write them in the Q&A tab and we'll try and get to them just before landing. But we'll also launch some polls for these trivia events.
All right, so which country on this list has not had a successful Mars mission? And it's a single answer.
So you can get your votes in, a couple of seconds for people to answer.
All right, so it looks like the majority answered Japan. And let's see if they were right. The correct answer was Japan. The Nozomi spacecraft performed a Mars flyby, but ultimately failed due to loss of fuel. So Japan does not have a successful landing.
Yeah, but this question really highlights just how international Mars science is. A large number of countries and partner nations have sent spacecraft. So it's the place to be.
There's a lot of ice locked up in Mars' polar caps. If you melted them all and spread the water out over the surface, how deep of a global ocean would it make? All right. It looks like we have people saying 1,000 meters, 100 meters. The answer is actually 20 meters, which is a lot of water. It's not 1,000 meters, but it's a lot of water.
And it's an interesting number, right? So these are Mars's modern ice reservoirs. This is the ice we see at the surface. But this mission is trying to target Mars's warmer, wetter past. And so to make a lake and big standing bodies of water on ancient Mars would have required more water than this. So what happened to that water? Well, it's been frittering off into space for the last several billion years. Without a protective magnetic field, Mars has actually had its water vapor and many of its lighter elements stripped off and pulled away. So Mars is a cold desert planet now, but may have been a warmer desert planet in the past.
All right, so we have a lovely group of winners for our next door prize. We have Lisa Reimer, Kristen Wilson, Anna Cook, and Chuck Higgins. Congratulations, you guys.
And again, we will get in touch with you about how to send these door prizes your way. So the next thing we want to look at is, what do we expect to see that's evidence for warmer, wetter conditions during Martian history? And so Jezero Crater, where Perseverance is heading, is going towards a lake deposit. But people have thought that Mars must have been warmer and wetter in the past, really since the Viking era in the late 70s and early 1980s. And the big giveaway for Mars not being the kind of boring desert world that we sometimes think of it as being is in the form of these valley networks, beautiful networks of valleys, much like the landscape around Hamilton here in New York, where rivers seem to have carved down into the Martian surface and left behind these sinuous, twisting, beautiful valleys. And this is Warrego Vallis, probably the most beautiful Martian valley network. And hey, panelists, so what do you notice about this valley network? What stands out about this Martian landscape?
I guess the absence of craters in that channelized area.
Awesome. Yeah, so the valleys are flowing between the craters. And so, any kind of moving water or wind on Earth can erase and erode features. So these impact craters may have been erased or cut through by these valleys, just like we saw at Jezero Crater. What else could you learn from these?
Well, it looks like the only craters that we're seeing are over top these valley networks, and it looks like they haven't been affected by the valleys. So maybe those craters that used to be there kind of resurfaced, but these new ones have formed since the water stopped flowing.
Absolutely. So Mars is an unimaginably ancient landscape. On Earth, we have plate tectonics that's constantly churning up the crust, making new crust, destroying old crust. Mars doesn't have plate tectonics. And so we can actually go to Mars to learn about 4.5 billion years of solar system history. Many of the surfaces, especially these ancient water-carved ones and ice-carved ones, are in cases billions of years old. And so they're really exciting targets to understand what planets were like early in the solar system's history, and all that evidence has been lost on Earth. So one real reason to go to Mars is to understand what was going on in the solar system early in its infancy. These valleys are big. They're kilometers across. They're kind of, some of them are Mohawk River size. People here in central New York with us, they're dendritic, so they look kind of like a tree or like a branching coral. And that's one of the clues that they may have been formed by melting precipitation, either melting snow like we've got going on outside today, or rain. So we're trying to get a glimpse into Mars's warmer, wetter past, but it may have been a kind of cold, wet. It may have been more like the Arctic or the Antarctic, where glaciers formed and ice flowed and then melted only during peak summertime. So we really don't know what we're going to see when we get there. We don't know what kind of climate clues are going to be hidden in Jezero Crater and in those delta deposits. As we fly back around, let's move on to more trivia and door prizes.
All right, so our next door prize, we have rovers. Winners are Joel Seif, Tom Bolanek, and Charlie Filipovich. Congratulations. And we have more trivia. So Mars's moons are named after what pair of classic Greek personifications? Fear and dread, hope and joy, trial and error, courage and fortitude, or chance and luck? All right, so it seems that most people chose courage and fortitude. Actually, Phobos and Deimos, Mars's moons, are named after fear and dread. So, yeah.
I think if NASA had named them, it would have been courage and fortitude. But these are pretty classically named worlds, and Phobos and Deimos, fear and dread, which we are all feeling a little bit of. It's okay to feel nervous on landing day. I feel nervous. Everyone at JPL feels nervous. I hope you feel nervous and excited too. This is an uncertain landing, like all Mars landings and all planetary missions. So hopefully it'll turn out well. It's been programmed to turn out well and checked and cross-checked. And some of the best engineers on the planet are working to get this rover down safely. So we'll know shortly.
All right, we have our next trivia question. It's on Martian atmospheres. What gas is present the most in the Martian atmosphere? Oxygen, carbon monoxide, methane, carbon dioxide, helium, or hydrogen? Okay, so we have our results. There is a very high preference for the answer carbon dioxide, which is right, because carbon dioxide is what primarily makes up the atmosphere. It's actually 95% by volume of the Martian atmosphere. Um, molecular nitrogen, trails behind with just 2.6%.
And were it not for life on Earth, this is pretty much what our atmosphere would look like too. And so, oxygen is one of these big markers of life as we know it, photosynthetic life. So we're hoping to find evidence of oxygen worked into minerals in the Jezero crater deposits. We also had a question about some of the instruments that the Perseverance rover is bringing, including one called MOXIE, which we'll talk about a little bit later today. But its mission is to actually test out a new technology to convert Martian carbon dioxide into oxygen, to actually crack off those oxygens so that future human explorers might be able to use this technology to get the oxygen that they'll need to breathe when doing operations on the Martian surface. So that CO2 is not so much a hazard as it is a potential resource for future Martians. And then I think one more trivia question in this round.
Yeah, before we get to some more prizes. So this one's about the size of the planet. So Mars is a little over half the size of Earth in diameter. If Earth were hollowed out, how many Marses could fit inside?
This would be if, Mars was silly putty. You could really cram in, make sure all the interstices were filled.
The poll shows that 4 is the most popular answer, but actually there would be 6 capable of fitting inside.
And so, yeah, the way I usually like to think about Mars, I've spent a decade or so looking at images of the Martian surface alongside members of the lab group here. And we never run out of Mars surface to explore. I mean, there's just so many beautiful high resolution images being returned, different spectra, topography, you name it. And there's always something new to learn. But imagine trying to understand the geology of every landmass on the Earth. That's about the surface area of Mars is the surface area of Earth's continents, so above the oceans. And so, as a land geologist, I can kind of wrap my head around like, okay, we need to understand everything on all these continents. And that's still more careers than anyone could imagine fulfilling in one lifetime. And so, yeah, there's always something amazing to learn about Mars. There are portions of the surface that no one has looked at yet. And so if you're interested in looking at the Martian surface, check out the HiRISE camera, HIRISE. It's the People's camera orbiting Mars today. A lot of the really highest resolution images you'll see come from that camera. And if there's a place that there's no imagery, you can request an image and be the first person to see some corner of Mars at its full resolution. So definitely check it out. And Nishraq, some door prizes.
Yeah, we have more door prizes this time. This one is for the terrain sampler poster, which has a lot of really pretty dunes on it, so you really want it, trust me. The winners are Caroline Todd, Daisy Yu, Tate Wright, and Jennifer Tomlinson.
Awesome. And these beautiful landforms. Oh, go ahead. have been imaged by the HiRISE camera. And so there really is something new to see everywhere on the surface of Mars. And I say it's a desert planet, but look at that variety. There's cracked ground and like permafrost. There's dunes like Ishraq mentioned. There's hills, there's yardangs, there's so many things to see. And the HiRISE camera and NASA make it possible.
It is very hard to count boulders on some of these. So.
This team has measured individual boulders across the Martian surface, more than 68,000 of them as part of a big project we've all been working on. And so these boulders are the size of, a car. And so imagine, counting cars in the biggest stadium parking lot for science. That's what the HiRISE camera enables, and some very hardworking student Mars scientists. So we're approaching about 15 minutes out from the real beginning of the entry, descent, and landing series. So I thought it'd be useful to talk about what's actually going to be dropped on the Martian surface today. And so this is a rendering of the Perseverance rover, and hopefully we'll get a chance to see this hardware delivered to the Martian surface. It's a pretty complicated looking machine. But it also looks familiar to a lot of other rovers we've sent before. So the Perseverance rover has 6 wheels, like most recent Mars rovers. That makes it very capable of negotiating rough terrain. Each of those wheels has its own motor in it. And so this is, slick weather is no problem for this rover. And the instruments for it are scattered around the deck of the rover, so the main body, on that mast in the back, and also on an articulated robotic arm that comes out at the front. And so we can kind of zoom in and look at some of these instruments and talk about what kind of science we hope to accomplish with them. And so this is a perspective view, now that arm fully extended. And MOXIE is that instrument mentioned a few minutes ago that is experimentally going to produce oxygen from Martian carbon dioxide. This is also the first rover to be bringing a radar to the surface of Mars. So there are orbiting radars that geologists might use to look for layering in rocks or underground aquifers if they're there. But this is the first time that a radar has been brought to the surface. And when you bring a radar down right to the ground, it's possible to get a much clearer view of what the rock is made of and how it's layered. And so these rocks at Jezero Crater are hopefully sedimentary rocks. So they're probably layered one on top of each other like a giant layer cake. And so RIMFAX is the radar that's going to help geologists on the rover team figure out how many layers are present in the rocks, what they're made out of, and what they might tell us about how water carries sediment to this basin. There's a bunch of cameras on the surface or on this rover. So there's the mast cam, which will take panoramic pictures of the surface to give a sense of where the rover is and what the geology looks like to create virtual outcrops. It's a stereo camera, so it's got 2 eyes for making sort of 3D renderings of the surface. It also has a series of different filters, so it can see in different wavelengths of light, not just the red, green, and blue like we see. What else have we got? Oh, there's a mass cam on the bench getting ready for assembly in the clean rooms and at JPL.
That's actually Colgate's own Megan Inch.
Oh, fantastic. And so Megan was part of the integration team that was working to take these cameras, which are just digital cameras like you would have in your cell phone, and actually get them hardened and toughened up and ready to work the first time, every time when they're there on Mars. There's no one there to press Control-Alt-Delete to get this rover to restart. And so a lot of the work is figuring out how to make sure all these systems work flawlessly. Can we jump back to the instrument overview? Awesome. We've also got SuperCam, which you might think is just another camera, but this is actually a laser micro imager. This is a system that's going to use a laser to blast rocks on Mars. And in the same way that, a sparkler for 4th of July produces different colored light, depending on what salts, what metals are in that sparkler, the rocks on Mars are going to glow in response to being zapped in different wavelengths of light. And so the SuperCam system is actually a telescope that's designed to zoom in on these laser flashes to tell people what the composition of the rocks are. This is a way that the rover can measure the composition of rocks and figure out what they're made out of and where they might have come from without having to get too close to it. You and I don't have a problem of bumping into rocks. But when you're sending a multi-billion-dollar rover to the surface of Mars, the last thing you want to do is drive it into a cliff. And so this is a way of not only finding out what the rocks are made of, but doing it really safely, doing it from a couple of feet back. We've also got a weather station here on the rover deck. So Mars meteorology is important not only for entry, descent, and landing, but also for understanding how modern climate is affecting Mars. So the META weather station is going to measure air pressure and temperature and other atmospheric variables. So this is a pretty fancy weather station, but is measuring the exact kinds of things that your backyard station might measure, or weather reports on Mars would use the exact same kind of information. I think this one also has a 3D wind detector, so it can measure not just which way the wind is blowing, but how it's swirling, which is pretty cool. And then out on the arm are the sort of a series of instruments that, again, tells what the rocks are made out of. Pixel is an X-ray spectrometer, and Sherlock is an ultraviolet spectrometer. These are imagers that look at the different wavelengths of light coming off these rocks, and every mineral has a unique fingerprint. So it's kind of appropriate that Sherlock is the name for this ultraviolet spectrometer. It's looking for the fingerprints of different minerals in the rock. Some of those minerals might be clays or carbonates. Those are minerals that form in wet environments on Earth, like a delta. And so they're going to be clues that this environment might have once been habitable, that it might have been a place where organisms could live. And piggybacked on the back here, maybe we have one little view of it, not in this image, but if there's something else, Joe, that you can bring up. We're also, this instrument is bringing the Ingenuity helicopter to Mars. This is the first helicopter system that will have ever been flown on another planet. It is not NASA's only helicopter. Dragonfly is going to be on its way to Titan soon. But this is a helicopter system, a lot like the kind of drone you might fly in your backyard here. It's a camera-equipped aircraft. It has 2 rotors so that it doesn't spin out of control. And hopefully it'll help provide some reconnaissance of the landing site. Again, a safe way to get high-resolution images that geologists can interpret. So if folks were tired of counting boulders on Mars with HiRISE, we can count pebbles with these Ingenuity images. And this is an exciting opportunity. Again, Mars's atmosphere is very, very thin, less than 1% the thickness of Earth's. And so this has to be a powerful and well-designed little electric engine and a very, very light aircraft to actually take off and fly around. So hopefully Perseverance will give it a wide berth. You never want to approach a drone with spinning propellers, and hopefully it will take off and be able to image the site. It'd be interesting to think about what that whirring sound would be like. A drone has a very characteristic kind of sound. See how that came through the microphones. Hopefully the microphones that are on the Perseverance rover will pick this up, and we'll know just how annoying it is to have a drone flying around your backyard on Mars. So an exciting technology demonstration, but again, also an opportunity to do some good science. And it'll be exciting to get the photographs and the videos. Flying around Mars, I think, is a dream for a lot of people. And so the engineers who put this together had a real vision that this would be a better way to explore Mars, that roving around is great, but flying would be even better. So we're running a little bit low on time before landing. Let's talk about the risks involved with this mission.
So
Bronson, take us away.
Historically, what are the odds that a Mars mission is successful? The poll should be popping up any minute.
While folks are answering that question, I did have a quick Q&A come in. The drone is, I think, Jessica's typing an answer. Perfect. Not super long is the short answer, but I think.
Oh, I just missed the answers. What's our most popular there?
It's the 33%.
Yeah.
That's correct. Yeah, so only 1/3 of Mars missions roughly have been successful in the past.
Lately, that has been improving. If there's anyone who can land a spacecraft on Mars, NASA and the Jet Propulsion Laboratory are some of the absolute best, but we will still have an exciting couple of minutes of TV ahead of us later this hour.
All right, and then our next question is, how long is a Martian day?
I'm just going to jump over to the NASA feed because we now have crew separation. So which means the spacecraft is heading towards the atmosphere.
This is going to go very quickly from here on out.
That's confirmation that we got shadowed by the cruise stage as it passed through our beam to the Earth.
Telecom indicated actually that we could see a signal that the cruise stage went between the Perseverance entry capsule and Earth. So we saw a little blip, the data stream indicating the cruise stage separation.
This is the equivalent of
confirmation that the vehicle has started warming up those entry thrusters. Warm-up pulses have begun.
Yeah, that is the equivalent of I've just driven into a tunnel. All of the spacecraft is communicating over radio waves, and so if something gets in the way,
is trying to stop
signal drops.
spin from the cruise 2 revolutions per minute down to 0, and then will turn to its desired orientation from entry. It will separate the 2 balance masses that has kept it balanced during all of cruise. This will allow the entry capsule to have lift when it enters the atmosphere. We have confirmation that the spacecraft has turned to the desired entry attitude. We're about 7.5 minutes from entry interface.
Okay, the vehicle is pointed in the right direction. The thruster.
All right, so going back to our question, I believe, can we see the answer to the poll? Thank you. Most people got it correct, 48%. It's about 40 minutes longer than our day, so 24 hours and 37 minutes. Good job, guys.
And this has a real consequence for some of the humans in that room that we just saw. The operations engineers and the science team that will be operating Perseverance from the moment it hits the ground have just entered into Mars time. So they're trying to give commands to the rover at the same time every morning when the relay satellites fly overhead. And what that means is they start coming in to work on a schedule that keeps shifting by 37 minutes every day. And that's going to have the consequence of they're going to slip through Earth days and their day is going to move around, whereas the rover is going to keep operating on regular Mars time. But that's important because that saves the rover power. It doesn't have to operate at night. It can just go to bed. But the problem is humans are trying to keep up with it are going to be out of sync. So it's going to be a bumpy couple of months for that team. But it's something they've discovered they really need to do to get the most science out of each rover.
All right, we have our next trivia question. The Earth is tilted 23.5 degrees along its rotational axis. How much does the Mars tilt on its axis?
And just give everybody an update. We have about 6 minutes to atmosphere entry.
And we have 2 contenders who for right answers from our audiences, 27 degrees and 25 degrees. But the correct answer is actually 25 degrees. It's also not a constant. The orbital tilt on Mars changes in a time scale of hundreds of thousands of years, and that is, in fact, one of the biggest reasons why the range of ice on Martian surface changes in history.
Yeah, Mars has ice ages just like Earth, and both these planets are solar-powered climate machines, so the tilt of the orbital axis governs the rise and fall of ice ages. So we've caught Mars at a really boring ice age-free time, but go back a few million years and it would have been hopping. All right, let's close out some door prizes.
All right, we have another set of rovers, and so there's 4 winners this time. Congratulations, Stacy Lowy, Susan Lapis, Jill Sommers, and Renee Chapin.
And all right, so now we have a couple questions from email from folks who registered. We've been trying to get some questions from the Q&A answered. So if you have questions in these last few minutes, definitely let us know, and we'll switch over to the live NASA feed. Amy Wasilik wants to know, what's the ultimate goal for these investments, and how will it change or transform human life? And that's one of the big questions about Mars exploration. Is it costs a lot. This is a multi-billion-dollar rover. All that money is spent on Earth, though. And that's one thing to keep in mind first and foremost, is that there's an old Far Side comic of money being loaded into a rocket and blasted off. But of course, this money pays for scientists and engineers, for material scientists who are learning how to build lighter weight, stronger materials, how to protect electronics from radiation. So NASA would usually say that there's a lot of technology investment that goes into spacecraft development, and that technologies from Velcro to cell phones have emerged from these kinds of missions that push the envelope on what materials can do. The other goal, right, is to answer big science questions. So was Mars ever warm and wet? Did life ever evolve there? What if it didn't, what made Mars different? And why did our planet become completely covered, pole to pole with life, and our neighbors didn't? And so these missions are motivated by that basic science question of, are we alone? And if we are, why? And if we aren't, what happened to everyone? And I think that would be pretty transformative. I think that, we're thinking about people in other NASA centers and around the world, in Texas, who have been suffering from storms, and there's a lot of suffering on Earth. And I don't think we should think about space exploration as being at odds with this. I think it's part of having a great civilization that will hopefully learn not only to explore the cosmos, but also to take care of our own people, and that these are 2 good things that good civilizations do. Edie Kolazar wants to know, will the samples retrieved at Mars by Perseverance require special transport once they arrive on Earth? And will temperature changes and atmospheric changes affect the research findings? So Percy is set to drill several cores of rock from the Martian surface. They're kind of pencil-sized rock cores, and they're going to be put into a sample holder. And then an upcoming mission, possibly from the US, possibly from the European Union with the US, will hopefully retrieve them and send them back. They're going to be packaged up pretty tightly. If you've had anything arrive broken, from UPS during the pandemic, you know that packaging really matters. And so these have been packaged to be both sterile, so we don't introduce any Earth microbes, but also strong, so that temperature swings from, for example, heating and cooling and sunlight in space, or re-entry, which is a warm process to say the least, doesn't damage them, because obviously you don't want to bake out any organic material, right? If there's anything, any evidence of life in this sample, you don't want to turn it into charcoal. You would want to see that it's actually there. And then let's see, folks on the panel, do you have any other questions you think that you like as favorites?
Hey, Joe, do you want to go to the live feed? We got 30 seconds.
All right, 30 seconds. All right. Type in more questions. We'll hopefully get to them after, and we're about to start the real heart racing part of this day.
5.3 kilometers per second at an altitude of about 150 kilometers from the surface of Mars.
Entry.
We have confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second at an altitude of about 120 kilometers from the surface of Mars.
So the goal is to slow down to 0 kilometers per second.
The spacecraft is now waiting until it begins feeling the atmosphere of Mars to slow it down. Once there is enough atmosphere, it will start controlling its path to the landing target. Navigation is also confirming that we can see a little bit of that slowdown of the atmosphere on the Perseverance entry capsule. Our current velocity is about 5.36 kilometers per second and an altitude of about 67 kilometers from the surface.
We are probably seeing MRO plasma blackout at this point.
So all of that hot compressed atmosphere on the spacecraft interferes with the radio waves. And so plasma blackout means no comms.
MRO has lost log.
Perseverance. We have indications that Perseverance is now performing bank reversals in the atmosphere. These are the steps in order to control its distance to the landing target. Perseverance has just passed through the point of maximum deceleration and has indicated that it felt approximately 10 Earth Gs of deceleration.
MRO has lock again.
Yes. 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 Yes.
We saw a small outage of the UHF telemetry from Mars Reconnaissance Orbiter during that peak heating phase, likely caused by the plasma blackout. Perseverance is still continuing to perform bank reversals in the atmosphere to control its distance to the landing target.
And so Perseverance actually has a camera-based system for looking at the terrain.
Going about 1 kilometers per second at an altitude of about 16 kilometers from the surface of Mars. We have entered heading alignment, which means Perseverance is no longer trying to control the distance to Mars, but to the target on Mars, but instead is flying straight to the target.
So again, there's no Mars GPS. So all of this is done by figuring out which way the spacecraft is pointed and which way it wants to go.
Our current velocity is about 550 meters per second at an altitude of about 15 kilometers from the surface.
MRO is reporting good telemetry log.
We are coming upon the straighten up. We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Yes. Yes. Yes.
The navigation has confirmed that the parachute has deployed and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
So parachutes are the first deceleration, and then eventually the sky crane will have its thrusters provide the rest of the deceleration.
Now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Yes, yes, yes.
Perseverance now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers of the surface.
And that radar will tell it when to fire its
On the
thrusters.
parachute, we are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
Almost there.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
So it's made a map of the landing site, and
current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN Safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver.
We've lost direct to Earth tones.
As expected. As expected.
Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO.
the Mars Reconnaissance Orbiter.
UHF is good. Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life. At this point, the descent stage has
That
settled.
never gets old.
Perseverance is continuing to transmit direct through Mars Reconnaissance Orbiter to Earth.
So everyone can breathe a little bit now.
Oh my God.
So yeah, this landing required multiple spacecraft, the actual
Still getting telemetry from
transit
middle
vehicle, the sky crane, the back shell, the parachute, and all of them seem to have worked flawlessly. That last maneuver is the sky crane literally flying away to crash someplace on the surface of Mars, not far away. And so it's done its job. It is no longer needed. And so now the rover has landed, and there's no, there's no things to unfold. There's no solar panels to get ready. This rover lands pretty much ready to do science. So once the dust is settled from this landing, we should be getting perhaps some of the landing photos back, perhaps some of that terrain relative navigation when it actually produced a map and figured out where it was going to touch down. And I think everyone's excited to see, are we on the floor of the crater? Are we up on the delta? Where did we just end up? And Perseverance is alive on the surface of Mars. So systems are go. Whew. How do folks feel?
Really good.
It is exciting. This has been, a lot of years in development and a lot of months in flight. And those have been long, hard months. And it's exciting to see this really coming to fruition. We had a couple of questions that, that certainly would be great to answer. And so thanks to folks on the panel for getting to some of those. I had a great question about what happens to the rover after the research ends. And, there's no going to pick them up. So hopefully someday these will be historical sites on Mars as these rovers further out. Their solar panels get covered or their radioisotope generators cool off. So it's pretty exciting. But hang tight, we also have our final door prizes to give away, and these will be celebratory given how exciting that last couple of minutes were. So now that we're here on Jezero Crater, Bronson, can you take us away and tell us what we've got?
Right. So our winners are Aaron Soul, Sharon Therese, Nick DeBrita, and Mark Jaschke.
It's a beautiful color composite of the Jezero Crater landing site and of that delta. We're there now, which is pretty cool. And then let's welcome Joe back, who's been our host behind the scenes and has put together all of these exquisite visuals and has programmed all of everything we've seen today. There's a real, I think, partnership between science and technology that we saw on display at NASA and that we have going on here at the Viz Lab, which is pretty exciting. So Joe has our final prizes, and let's thank him again for putting together such an awesome event.
No, my pleasure. And thank you to all the panelists, and thanks to Joe for leading us into great science talk and answering questions from all of our viewers and attendees. So our last door prize is actually a little piece of Mars itself. We have 4 little Martian meteorites to give away. And the winners of these, I'll start Lynn, is Matthew Dirting, actually the Venus twins, Matthew and Jake Dirting. Next up, we have Ephraim Woods, and then Brent Hatton. And our last one is Corinne Centauri. So congratulations to you folks, and congratulations to all the door prize winners. So, and again, thank you for tuning in. I think, Joe, maybe we can answer the last few questions.
Absolutely. One quick update from the surface. The HazCams, the hazard cameras on the rover, have fired up and the ground is level. The rover is the right way up. That's something you need to know, and now we know it. And it is casting a lovely shadow on the Martian surface. So we are there. Let's see, we have several of these questions have been answered in text form. Looks like we have maybe 2 open questions. We have 3.5-year-old Sabine wanting to know who's allowed to drive the car and the Perseverance rover. And these spacecraft will be driven from Earth, from the Jet Propulsion Laboratory. On the moon, you can drive a rover with a joystick. The time delay is such that you could actually just sit there and control it. We're something more than 11 minutes of light speed travel between Earth and Mars right now. And so the science team will be coming up with instructions every day for the rover, and they'll upload the instructions and it'll go. Perseverance can actually do a little bit of thinking on its own and avoiding hazards on its own, which is pretty cool. Sabine, if you grow up and can bring a steering module to Mars, I think you have my permission to put that on and drive it around. Hopefully it'll still be going strong. So that seems totally fine with me. Other questions we're missing, or do folks feel pretty good?
Joe, I was curious what you had to say about William's question.
Oh, yeah. So William Peck has asked, if there's evidence good for flowing water here, why wasn't it a target for future missions or for past missions? So Jezero has been, Crater has been a target for a long time now. It did not make it through the bake-off that happens when the science community helps pick Mars landing sites. And so, these sites get picked by the Mars science community getting together and talking and debating and trying to make the best possible case. So Jezero Crater is right next to another landing site that called Isidis, that didn't make the cut, but was a real strong contender for showing different kinds of geology. And so, for whatever reason, hazards, the size of the landing ellipse, the safety for actually getting the rover there, or the priority of the science question, Jezero wasn't picked. And then this time it's had its moment in the sun. And so hopefully this will be opening up a new kind of exploration of Mars's sediment and water record. The Earth system is that interplay between sunlight, gases in the atmosphere, ice, water, life, all those things. And we think that might be true for ancient Mars too. So hopefully this is the start of a whole new kind of Mars science. Can't wait to see what the rover finds. I'm really excited. Well, and thanks to everyone for coming. It was just great spending the afternoon with you. Thanks again to the panelists. It was great to see you all and to have you helping drive and answer questions and make this a fun event. And thanks again to Joe and the Viz Lab for making this happen. And thanks to NASA and JPL. And I guess we'll see you all on Mars sometime again soon.